Okay, we have a cylindrical lens viewed from the top, so we just see the circular profile. We have a central ray, goes through the center of the circle. Circle has radius r. We have a ray coming in at a distance delta x from the axis and parallel to the axis. Now, we've drawn delta x much bigger than we really want it to be, just so we can label the diagram. We're assuming that delta x is much smaller than the radius r, so that we're going to be able to use small angle approximations throughout our analysis. So what we want to do is we want to figure out what happens when this ray strikes the cylinder. And let's say that the cylinder, we have index of refraction m inside the cylinder, and index of refraction 1 on the outside of the cylinder. So in the experiment we're doing, we actually have water here where the index of refraction is about 1.33, air where the index of refraction doesn't differ significantly from 1, at least not significantly for the accuracy of the experiment itself. Okay, so what happens? Well, the ray comes in here. We're moving from a point of index of refraction 1, which is the smallest possible index of refraction, to an index of refraction that's not 1. Okay, and so it's greater than 1. Now, the angle of incidence of this ray is theta sub I, and that's the angle that the ray makes with the radial line. The reason being that the radial line is perpendicular to the part of the lens that the incoming ray encounters. So we get an index of refraction, and of course we know how refraction works. The ray refracts at a smaller angle, and that refraction might look something like this. So we have an angle of refraction theta sub r. We get to the back of the lens, and here we have another refraction. There's our radial line and our tangent line. So that the ray is refracted to a larger angle with respect to with respect to the normal. Excuse me, I just realized something and wanted to think that through. Okay, so not completely relevant to this, but kind of distracting. Okay, so we have now an angle that I'll call theta sub I prime. So that says theta sub I prime here. And when we refract, we're going to refract, since we're going from an index of greater to an index of lesser refraction, we're going to refract away from the normal line. And we'll get some angle of refraction that we'll call theta sub r prime. And extend that just a little bit. And that's going to cross the axis at some point. So we want to be able to figure out what all these angles are, and then do the arithmetic and figure out the distance here behind the lens at which this ray actually intercepts the axis. And that will be what we would regard as the focal point of this lens. At least the focal point in as much as the lens has a focal point. For any lens, the focal point is the point at which rays close to the axis and parallel to the axis converge. I'll also comment that for some substances, this ray could actually cross the axis before it hits the back of the cylinder. but for water and for most substances, the index of refraction is low enough that that doesn't happen. And when that does happen, then the focal point is actually inside the lens. Okay, well, let's make a few small angle approximations here. Okay, let's go ahead and use different colored chalk to do that. First of all, theta sub I. What is the angle theta sub I? Okay, well, the radial line here, again, this figure doesn't really show it, but this ray should be much closer to the axis than it's drawn in any case. Okay, I could draw a triangle here, and we see that this distance here is delta x. This distance here isn't quite equal to r, but for rays close to the center, it's practically equal to r. So that we have, first of all, the sine of, I'll call it this angle here. Well, let's just let the cat out of the bag. This angle here is the same as theta sub I. Okay, of course, theta sub I occurs out here, but we have two parallel lines here, and this is this radial line is a transversal. So we have the sine of theta sub I equals delta x over r. Well, by small angle approximations, it means that theta sub I is delta x over r. Now, theta sub I equals delta x over r doesn't occur for angles in degrees. Angles are not measured in degrees unless they're specified in degrees. When an angle is given as a pure number, then that angle is regarded to be in radians. That's the definition of angle. That's the mathematical definition of angle. Okay, so when we do calculus, when we do really much of anything with any depth, we usually don't do it in degrees. We usually do it in radians for many reasons, the small angle approximation being only one. Okay, so we have theta sub I equals delta x over r. There's our angle of incidence. Now, what's our angle of refraction? Well, our angle of refraction, and I'll kind of write this in small, just write it in white over here. We have sine of theta sub r over the sine of theta sub I equals what? It equals 1 over n by Snell's law. Again, the index of refraction n goes in the opposite part of the fraction from the angle inside the lens. Okay. Well, by small angle approximation, that tells us that theta r over theta I equals 1 over n. So the angle of refraction is theta I divided by n. So theta r equals theta I divided by n. Now, we need to figure out, we know now the direction of the ray as it goes through the cylinder. We need to figure out how close the ray gets to the axis, or alternatively how far it gets from the line of the original ray. So grab another colored chalk. Where is it? Okay. So we have this angle here being theta I minus theta r. This distance, for the same reason that this leg of the triangle is close to r. If delta x is small, there's very little difference. This leg of the triangle is going to be 2r, or very close to 2r. So that this leg of the triangle, which will actually extend much closer to here. My circle isn't very well drawn at that point. This leg of the triangle is going to be equal to this distance, which would be the hypotenuse, multiplied by the sine of theta sub I minus theta sub r, or alternatively by this 2r times the tangent of theta sub I minus theta sub r. So I'm going to write this distance here, and let's call this, don't want to call it a delta x because that doesn't do much. Let's just call this distance A. Okay, so we can say that that distance A equals 2r times the tangent of theta I minus theta r. Now the tangent for small angles is pretty much equal to the sine because the cosine of a small angle is very close to 0, very close to 1. Cosine of angle 0 is 1. So that's going to be just 2r times theta I minus theta sub r. Okay, which means now that the distance between the axis and the point of intersection here is, kind of draw that in purple, and it's going to be really small, and I'm probably blocking the board, but that is going to be delta x minus a. That's going to be this distance. You can't really see that there. It's not drawn very well. I should have made this thing about halfway between here and here. I just kind of aimed it a little bit carelessly. In any case, that distance is delta x minus a. Now at this point I want to redraw a little bit of what we have over here just so we can see it. So I'm going to do that off camera. Okay, again, this little triangle up here, I've kind of made it a little bit fatter, where we have the delta x minus a here, which is just the delta x minus the a being the displacement of the ray as it moves through the lens in this the displacement in the what we might call the vertical direction, displacement perpendicular to the axis, excuse me, within the lens. So there's our triangle. We have this side is r, or very close to r. Get out of the way so I'm not blocking it. Now this angle here is just, well, the sine of the angle or the tangent of the angle is x minus a over r, which means that the angle in radians, being a small angle, is delta x minus a over r. Now remember, a is an expression down here. I'm just using a to kind of hold that expression for the moment. We'll come down to what that really says in a minute. Okay, so we have delta x minus a over r here. Now we have angle theta I minus theta sub r, which is the angle made by the original direction, what we would regard as the horizontal direction, even the x direction, with the ray as it approaches this point. So here's your angle theta I minus theta sub r. I've drawn a dotted line that's intended to be parallel to the axis. And we have theta sub I prime, which is our angle of incidence, the angle of the incoming ray with the perpendicular to the tangent plane. And I'm not going to draw the tangent plane here, but it's going to be perpendicular to the radial line, and hopefully we understand this. I will draw that when we draw the final picture. Okay, so here we have everything we need to determine the angle of incidence, because every symbol here represents something that we have symbols for in terms of the delta x and the r. So we're going to put that all together, but we'll put that together in another video because this one's almost too long.